Okay, well, thank you everyone for joining us this afternoon. I think it could be our first LJC afternoon event. Quite well signed up to so far, so it could be something for the future. Do let us know about the timing. So I'm just going to say a few words, and then I will get out of Nikki's way. My name is Barry Cranford. I'm the founder of the LJC. Also known as the London Java User Group. So just to give you a bit of background about this, if this is your first LJC event, or if you're tuning in afterwards from around the world, the numbers behind the LJC, which kind of give a bit of context, we're 13 years old now. We've got just approaching 7,500 members, and we've organized over 600 events. But beyond the numbers, what really makes the LJC what it is the values that exist within it. We're very much around mentoring, really a true community, and trying to bring everyone together to benefit. There's lots of other things that have come out of the LJC, or the LJC's given birth to, loads of other technical communities in London, Adopt Open JDK, Adopt JSR, there's loads of different initiatives. If you want to learn more about it, then go and have a look on our website. So as for who I am, as I say, I'm the founder of the LJC. I'm not a developer myself. I can't even write hello world in Java, I'm ashamed to say. I am in fact a recruiter, or I run a recruitment company called RecWorks. So as for who we are, I know a lot of you out there will know of us. So we are a tech recruitment company, and we are built around this core belief that recruitment can be a force of good, a power of good in the industry beyond just getting people jobs. So a lot of work that we do sits somewhere between giving back to people that we've worked with in the past and paying it forward for people that we hope to work with in the future. So a few examples of some of the things that we do beyond just placing people. We've run the 600 events in the LJC, of course, but a lot of other technical communities, student communities, graduate communities, CTO communities, lots of other things that we do there. We've made over 2,000 mentor to mentee introductions, direct one-to-one introductions now over the last 3 years. And most recently, we started a new aspiring speakers group, which actually Robin's going to be helping us with hopefully later this week. So we have a small group, about 20 or 30, I think, people that are looking to get onto the conference circuit. So if there's anybody out there that does want to be the next Robin or the next Nikki, then please hit me up on LinkedIn or Twitter or anything, and come find me afterwards. So it's all powered by recruitment, and what that means is we don't make any money other than the money we make from getting people jobs. So if there is anyone out there that's looking for work, anyone that's looking at hiring even now or in the coming months, give us a shout, and yeah, we'll be happy to work with you. Anyway, getting out of Nikki's hair, as I say, Nikki is the CTO for Open Credo, and she is today she's going to say a few things to introduce herself in a minute, but today going to be speaking on using graph theory to explore your microservice architecture. So Nikki, enjoy.
Cool. All right, thank you. So let me share my screen, or actually let's start this, that one. All right, I've got to press play. All right, can you all see that? Excellent. Okay, great. Yes, so delighted to be here this afternoon. So I think the way we probably do this is I probably give the talk, and then happy to take sort of questions afterwards. So I know different people do it differently. Some people kind of do questions along the way, but I think if you type your questions into the chat or whatever, and we can catch them afterwards and then grab them there. So yeah, so I'm going to be speaking about how you can use graph theory to explore your microservices. So I'll start with just a little bit of an introduction about myself. So my name is Nikki Watt, and as Barry said, I'm the CTO at a company called Open Credo, and we're a hands-on software development consultancy. So we help our clients to adapt and adopt emerging technologies to solve their business problems. And we tend to focus in two main areas. So the one is the sort of cloud native microservice sort of space, and the other one is on sort of data engineering platforms. And quite a few of the sort of projects that we've worked on have been in the connected data space. So this has been around things like maybe social or political networks, where you want to try and understand like how are people connected to each other and sort of relationships between them, or even ethical supply chain management. So this is where you have, you know, you're building some product and it's composed of other sort of resources, and you want to know where have they come from and are they ethically supplied, and also things like physical infrastructure networks. So, and we've done a fair amount of work in Neo4j. So what I want to really do with this talk is try and look at combine these two areas and see, can we take some of the sort of the techniques and the algorithms and things that we've used to solve some of the business sort of challenges for our clients, can we use that to gain some insights by looking at a microservices architecture in the same way? So, why is this not moving forward? There we go. All right. So the first sort of 15 minutes or so, we're going to probably go through a little bit of an introduction. And we're going to cover just a little bit of sort of theory, because we'll need that just to understand the sort of application of it sort of moving forward. But we'll cover things like, you know, why am I doing this talk in the first place? Why am I trying to bring these things together? And then take the theory for a few of the metrics that we're going to have a look at from graph theory, and then practically apply that onto a microservice architecture and see if we can get some insights out of that. So, okay, I must press that. All right, so from the introduction perspective, I guess the first thing I'd like to say is that there's already quite a few places within sort of general software systems where graphs are already used to drive out efficiencies in software systems. And good examples of this is in the code space, or one of the examples in the code space. So if you're in the Java space, as you probably are in the Java community, you'll be using things like Maven. So this is to manage your software dependencies within the code. You're probably using something like IntelliJ as well, and you might use some of the features in there to maybe have a look at circular dependencies of some of the packages and things that you have. Likewise, if you have a CI/CD pipeline, you might want to analyze some of the software vulnerabilities that you have in maybe your open source packages. So that can be done through a tool, for example, called SNCC. And that tool also allows you to do things like look at open source violations in your code. So you may have libraries which are within libraries, which are within libraries. And the key, I guess the key sort of thing here is that under the covers, all of these are using graphs in various ways to be able to give you insight into the code within your system. So at a code level, that's some examples of where graphs and some of the sort of graph theory is being used. Then there's also the sort of cloud and infrastructure layer. So this is where an example like Terraform is actually a really good example of where graph and graph theory is used. So for those of you who maybe aren't quite so familiar with Terraform, Terraform is a tool from HashiCorp which allows you to create or define the infrastructure that you want to create in a cloud provider like Amazon. You run Terraform over the definition that you have, and then it makes sure that those resources are created for you in the cloud. But under the cover, the way Terraform actually works is that it creates a graph of all of the resources that you're trying to create as a directed acyclic graph, and then it uses that to be able to work out how it can do things maybe in parallel in order to speed things up, as well as making sure that things are done in the correct order. So here again, you've got an example of core sort of graph theory, which is being used in the infrastructure and operational space. And then also there's the sort of ops and monitoring side of things. So if you, hopefully, if you're working in the microservices space, you're already working with some of these tools. So these are tools like the various distributed tracing tools. So you've got the Open Tracing API, and you've got tools like Zipkin and Jaeger. And they can be really helpful in giving you insights into maybe some latency analysis where things are going a little bit slow. Have a look at your microservice paths and really give you insight into the system. So again, under the covers, if you have a look at what's going on in some of these tools, the sort of spans and the traces are really heavily based on modeling of a graph. And you can visualize your entire sort of microservice architecture with some of these tools. It is quite powerful to actually be able to allow you to see what's calling what when you're trying to troubleshoot things. So really powerful from a troubleshooting perspective. So given that we already know that we've got some of these tools out there that can give us insight into the code and maybe the infrastructure and these type of areas within our systems, what I want to see is can we actually use it to drive improvements in our microservice architecture? And the way that we'd probably look at doing that is, so this is just a shout out to a guy called Adam Thornhill. So he actually gave a talk at GOTOcph Copenhagen, which was, I think it was last year, end of last year, but he was looking at the connectedness of microservice architectures. And one of the important things that he notes is that it's not so important to look at maybe the individual properties of the microservices and the nodes that you have, but often it's the properties of the system as a whole. And when it comes to graph theory, that's looking at the relationships as well. So what I want to look at doing now is say that I believe that there's a hypothesis that I want to put forward, and that I think it should be possible for us to start moving towards what I would call data-driven architectural improvements. So we've already seen that you can extract metrics and KPIs from microservice architectures through tools like tracing and things like that. But I think what you can do is build on top of this and add another angle to your sort of toolbox of things to analyze your system with. And that's by using graph theory to extract some of that information and then do the analysis on top of that. So, and this will hopefully give you some insight into your microservices architecture. So for this talk, we could venture into a few different directions. So to try and make it a little bit more concrete, I want to take a sort of specific case and have a look at a few specific metrics and see, can we use some of the metrics from graph theory to be able to detect maybe some bad architectural smells? So this is something like a tightly coupled architecture. So as a consultancy, we're often called into clients to help them out with building systems. And sometimes this will happen where we go in right from day one and we can guide them and sort of steer them in the right direction right from day one. But sometimes we also get called in when things have gone a little bit wrong. And often one of the prime suspects when we kind of looking at some of the microservice systems is that they tend to have a very tightly coupled architecture. So it's quite helpful to try and see, are there some ways that we can have a look at detecting this in a more data-driven approach rather than just pure gut feel. So now we're going to look at maybe just a little bit of quick graph theory. It's not going to be major maths, so you don't need to worry too much about that, but just enough so that we can understand what's going on. So I guess the first thing is really just to say, like, what is a graph and what is graph theory? So really, it's just a formal way to represent a network or collection of objects in a mathematical way. You have the nodes or the entities in your graph, which are often called nodes or vertices. Then you also have the relationships between them, and these are often called edges or just relationships. And as I said before, this can be examples of networks or social networks, infrastructure networks. But in our case, we're going to model our microservice architecture with a graph. So in this case, the individual nodes are going to be the actual microservices themselves. And the relationships will be the calling path between them. So if you've got microservice A, which is calling B, which is calling C, that's the relationships that we're going to be modeling here and that we're going to have a look at. And it's probably worth saying that for the one that we are going to have a look at the moment, it's, or at least in version 1, it's sort of HTTP calls that we're going to be having a looking at, RPC type calls. So how do you then go about getting insights from a graph? So there's typically 2 ways or 2 parts to this. So there's the graph analytics, and then there's the actual algorithms that you use. So with graph analytics, this is really just the actions that you perform on the graph in order to have a look at how it's connected. And once you have that, there's a variety of things you can do. One of the most powerful tools is actually just to be able to visualize the graph in the first place. So quite often, just by being able to gather the information and visualize it for a human, it provides a lot of insight for people to do pattern recognition just at a human level and actually recognize things in and of itself. But often what's more sort of powerful is to use some of the graph algorithms and we'll go into some of them, that you can actually run across the network. And this will use some of the mathematical properties that you get from a graph in order to give you insights into the way that the graph is actually structured and allow you to infer some characteristics about your setup. So let's, I'm now briefly going to take you through 3 specific measures that we're going to use as part of this talk. But before that, it's probably worth saying that there's, roughly speaking, the sort of algorithms, the graph algorithms are probably categorized in about 3 categories. So you've got a pathfinding category, you've got a centrality category, and you've also got something called community detection. So we're not really going to focus on the pathfinding algorithms for this talk, but that includes things like shortest path. So a good example is, for example, if you're on the tube, which you shouldn't be during this lockdown, but maybe you want to find out, what is the shortest way for me to get from, point A to point B. A shortest path algorithm will allow you to find that. We're more going to be focusing on what are called the centrality and the community detection algorithms. And with centrality, this is really about trying to find out how important or significant a node is within a network. Like, does it have a lot of traffic flowing through it, or does it facilitate traffic sort of moving through it? And then on the community detection side, that just helps us to uncover structures or related groups or clusters within the network, which can also be quite helpful. So the first metric that we're going to have a look at is something called the degree of a node. And this is really just about how connected a specific node is. So if we have a look at the nodes over here, we can see that node A is more highly connected than B and C, because it's got basically 6 connections either coming into or going out of it, whereas B and C have only got 2. And with a microservices sort of architecture, this metric can be one potential indicator to us as to how busy a particular service is. So if a service has got a lot of calls either coming in or going out of it, you know that there's a fair amount of traffic that's going to be going through that node. So that's the one metric that we're going to be having a look at. The other one is something called a cluster coefficient. So the cluster coefficient is really for measuring how tightly grouped a cluster is compared to how tightly grouped it could be. So this is sometimes a little bit, or sounds a little bit abstract to people. So I'm going to give you an example to try and explain this a little bit better. So if we were to take this as a social network and we said this is a group of friends and we've got this blue person here, what we want to say is that we know that the blue person knows 3 people, but what we really want to ask is how well do all 4 of those people actually know each other? And this is calculated with something called a cluster coefficient. And it's always calculated relative to one of the nodes, in this case, the blue node. So we note that out of the blue node's friends, most of them sort of know each other, but actually the top person doesn't really know the bottom person and vice versa. So when you calculate the cluster coefficient for this particular group of nodes, it comes out at about 0.66, or basically it says about 66, there's about a 66% probability that all of the people in that group will know each other. So if you compare that to the blue person on the left in the other group, that blue person also knows 3 people. But in this case, all 4 people actually know each other. So the orange people also know each other, and therefore the cluster coefficient comes out at 1, or essentially 100%, saying that this is a completely tight-knit group of friends. They all absolutely know each other. And again, the application for us, if we transfer this into a microservice network, is that it can be used to detect a lot of chattiness amongst a particular group of microservices. So this might be an indicator if we find high levels of cluster coefficients of groups of services that we might want to take a bit of a closer look at. So the last metric, or the last sort of group of algorithms that we're going to look at, is something called community detection. And this is a family of algorithms, so there's a variety of them. And generally they are used to find related communities, uncover groupings, and quantify how good some of those groupings are. So the general principle with this is that you take one of these algorithms and you run it across your whole network. And then the system itself would work out, or the algorithm would work out what it thinks groupings of nodes are. So it might say, well, I think there's this purple grouping of nodes that seem to be related together, and there's an orange group. And then you as a human, after that detection has been done, get the opportunity to look at the groupings and try and make sense of it. So you might say, for example, oh, those purple ones, maybe that seems to be a bounded context around a particular area. Maybe it's payment stuff or something like that. And the orange stuff seems to be, I don't know, all of the legacy stuff that we're dealing with. But it would be up to you as a human to make sense of the groupings that the algorithm comes back with. So we've now set the scene. We've got our metrics that we've got a basic sort of understanding of. Now we're going to dive in and see how can we actually apply that on a microservice architecture to see if we can gain some insights out of that. So the first version of the microservice architecture I'm going to show you is a really small one. So it's only got 23 services in it, and it comes from sort of commerce and retail domain. And as I said before, in this version of the architecture, there's only sort of synchronous RPC calls happening amongst the services. So here is a rendition of the wonderful architecture. Now you don't need to worry at this point in time that you understand it. You don't need to understand it at this point. But the key point to understand here is that the first goal that you would need to try and achieve in terms of getting insight is that you need some way to be able to get all of your microservices, sort of get it out of people's heads and things and actually into a database, model it, put it in a database, and then allow it to be analyzed. So the example that I've got here is it's actually been put into a database called Neo4j, which is specifically to handle graph-related setups. But you can use other things like various other databases or even Python. So the question is, how do you go about getting the information into something that you can then analyze? So the one option is to do it statically, and that's how this particular one has been done. So it's small enough that if you're an architect or you know the system, you could say, well, I know there are these services, and I know that this one calls this one in this case, and you could actually model it and capture that information in the database yourself. But there's a lot of problems with that because it's quite subjective. You may be wrong in your understanding of the system. So a much better way to do it is to try and dynamically actually extract the information into the area that you want to do the analysis. And there's a few ways that you can do that, but it's quite dependent on the setup that you have. So there's no one size fits all that you can just, run a tool and it'll magically work for everything. So sometimes people, you can use things like Zipkin, or if you've got some kind of distributed tracing tool already in place in your microservice architecture, you can hook into some of the sort of tracing that comes through that and use that to be able to extract the calls that are being made and actually build up a rendition of the model that you have. If you're using something like a service mesh, maybe like Istio or something like that, you could potentially hook into the mixer and get the information out that way. Or maybe even through CI/CD pipelines as you're actually deploying, you could try and do it that way, but better to try and get dynamic information if you have it. So we've got our network of microservice sort of in the database, and if we run our network stats, we get something like this. So this is a table which will show for each of the services what the degree is of that individual node. And it can split it out into incoming degrees and outgoing, as well as the cluster coefficient. But it's quite hard to just look at the numbers here and try and make sense of it. So often it's, oh, someone's got a dog in the background. No worries.
All right.
That's okay. Often it's better to chart that out because it gives you a little bit more of a visualization of what's going on. So if we look at this in a chart, we can see that for the majority or the half of the microservices, they don't even register much in terms of their degree. It's basically about 1. But for the top 6, which are the bottom ones on the diagram here, they've got a degree of 6 or more. And this is, network that's only got about 23 nodes is potentially quite a lot. So what this says to us is that we're not sure yet, but maybe those 6 at the bottom that have got a degree of 6 or more, maybe there's something going on there. Seems to indicate that they're doing a lot of work. There's either a lot of calls going into or coming out of them. So maybe we need to look a little bit closer at that. If we have a look at the cluster coefficient, do the same thing for that and put it on a chart. Again, we can see that more than sort of half of them don't even register. They've got a 0 cluster coefficient. But the top sort of 7 offenders have a cluster coefficient of 0.6 or above. So again, this is another indicator to us that maybe those services that have got this high cluster coefficient, they seem to be really kind of talking a lot amongst themselves. And the combination of a high degree and a high cluster coefficient, maybe those ones we also need to have a little bit of a closer look at. So as I said, we've run these metrics and we've been directed at a few services that seem to have some high values. Now we need to try and work out, is there actually a problem or not? And at this point in time, you probably need to obtain like some kind of architectural knowledge in order to actually apply the information that's coming out of the metrics onto the real world or the reality that you find yourself in. So here we have an architectural diagram that an architect gave us, or a sort of overview of the system, which shows us how the system is, from their perspective, being kind of put together. So again, you don't need to really understand the low-level details of this, but if you have a look at the broad sort of colorings, you can see that we've got the dark blue microservices, which are really the front-end services where the end clients will come in. So these are things like your mobile API, web API, and your sort of B2B API. You've then got the light blue services at the back, which are the back-end services. And this is where a lot of the main sort of work would be done. And you've also got some pink/purple type sort of nodes, which are the ones that are dedicated to doing external integrations. So there's a bunch that does stuff in the shipping for integrating with different shipping APIs like DHL and stuff. And then you've got other ones that are integrating to various payment services as well. But what we already notice is that on the right-hand side, there seems to be what I would call a big ball of mud. So a lot of services that are making calls amongst each other. And even the architect at this point is like, actually, you know, there's probably something, you know, there's something going on there. But what we really want to find out is that even if you intuitively know that there's potentially something going on, can we use some of the metrics that we've had a look at? Will it actually identify that as a problem for us as well? So if we take the degrees that were the top sort of degrees, and we highlight which of those nodes were problematic, we can see that it's mostly all of the backend services that have been highlighted. And most of them are actually in the big ball of mud already. So the ones that were highlighted as potentially problematic are also the ones that are intuitively the ones in the big ball of mud that we think we need to have a closer look at. If we have a look at the cluster coefficient, we can see that for the top 7 nodes that had a cluster coefficient of 0.6 or more, they also, the majority of the nodes which have been identified are the ones in the big ball of mud. But this time it's not just the back-end ones, it's also got the front-end services at the top. And you might expect that if a call comes in through, through some kind of web front end, that it is obviously going to make a call to a lot of back-end services. So that's not necessarily a problem in and of itself. But what you probably wouldn't want, or you wouldn't expect, is that all of those microservices behind the scene themselves are making calls amongst themselves as well. So this is a potential sort of indicator of a problem to us. So what can be quite tempting to do with some of these metrics is to just use things like averages. So you could run and calculate the average degree across the whole network, as well as the cluster coefficient, and it would come out as something like this, so sort of 3.6 or 0.3. But often this is not really that helpful in trying to gain insight, because all it really does is just hide some of the sort of problematic areas. So what you really rather want to do is look at some of the top and the top offenders, or even low values sometimes, to see whether those are the areas that you want to have a look at. So averages can be helpful, but I'd argue in this case, not that helpful. So when you take a little bit of a closer look at this particular architecture, so putting aside all of the metrics and everything and just understand what is going on in the architecture, we can see that something has gone wrong, and it is exhibiting signs of what is called an entity services anti-pattern. Now, this can happen for many reasons in a microservice architecture. But one of the sort of key factors that we found anyway in terms of the consultancy that we do is that sometimes when people start maybe building their systems as a microservice architecture from day one, if you come from a more sort of classical understanding of how systems work in a monolithic sort of setup, it's quite easy to decompose them into some of the entities that you're used to working with when you were working in a monolith. But what happens is that if you look closer at some of the backend services that we've got in our architecture here, they have very much been modeled after entities. So you have things like an order, you have a user, and you have a product. So these are classic entities, and is quite problematic in a microservice architecture because you land up with what's sometimes called a distributed monolith. So the problem here is if you think about trying to do a particular function within the system, so maybe you're trying to make an order. So the call would come in through the front-end microservice. And then in order to just order a product, you might have to call the order service. And then the order service itself would say, well, I don't have all the information about the products, and it calls the product service. And then it lands up calling the user service. And it lands up having multiple calls happening just to fulfill one very simple, relatively sort of simple functional request that has come in. And this is when you design systems with, or when they come out with an entity services sort of anti-pattern, you land up with a very, very chatty architecture. And this is symptomatic of what we're seeing here. Now, the one thing I do want to point out at this point is that these metrics are not going to be able to tell you that you have an entity services anti-pattern in your architecture. All it's able to do is point at a few different services and say, it seems like these ones are exhibiting these properties. For us, it was only by having the sort of architectural knowledge, having a look and analyzing the system itself, that we recognize that, oh, actually, in this particular case, the reason why it's so chatty is because it's been modeled with this entity services anti-pattern. So that's just something to be aware of. So don't think, oh, I can detect exactly when it's an entity service anti-pattern and not. That's not necessarily the case. You still need to use sort of architectural knowledge to work that out. So, and a word of warning as well, you also can't use some of these metrics blindly. So generally, I'd say for some of the stuff, you need to look at using the degree and the cluster coefficient in combination. So just because one service happens to have a high degree doesn't necessarily mean it's problematic. There could be a lot of good reasons for that. But when you combine it with something like the cluster coefficient, then it gives you a better view of the world. And it's always very context dependent. So just because a degree of 6 in this particular architecture was problematic doesn't make it problematic in a different one. There might be a lot more services in that. They might have different characteristics. And that's just something to be aware of. So the last sort of family that we haven't had a look at yet is the community detection. So if you recall, what the community detection will do is it will have a look at classifying different parts of your architecture into different groupings. So when we run this, we want to have a look and say, well, does it also seem to indicate that we've got a problem in the big ball of mud? And here we've got two graphs which are essentially exactly the same thing. So the one on the left was done in a Jupyter notebook with Python, but it's quite hard to see what's going on. So I've just superimposed the coloring of the groupings that were found onto our architecture. But they're essentially the same thing. And you can see that when we ran the community detection algorithm, and in this case, it was Louvain modularity for those that are interested, it found 3 areas. So it certainly did highlight the big ball of mud in the red area, but it's also highlighted the fact that there seems to be a yellow bit, which if we look at it as sort of architecture, we'd say, ah, well, that seems to be the area that's doing all of the shipping related stuff. And the purple stuff seems to be the area that's doing the payment related things. So it has actually highlighted that, which is good for us. But it's confirmed that the monolithic sort of problem is problematic. But what is maybe sort of interesting is that this might not be what the original architect was actually intending. So when you're designing microservice systems, you're often trying to create bounded contexts and do domain-driven design. So the intention in the beginning was probably not to create something that was this tightly coupled. It was probably more around wanting to have something where, you know, users or user management was dealt with separately compared to products and stuff like that. But if we have a look at what the algorithm has sort of detected, it's quite different to what may be in people's minds. And this can be a helpful way to actually give you some insight into a system that you don't necessarily have that much knowledge of, to see how it thinks things are actually related to one another. So I quite like this slide, so I put it in here. It's a little bit tongue-in-cheek, but I do love the picture. As I said, the algorithms are not necessarily going to always detect your nice, pretty domain-driven design bounded contexts. What you might find is that sometimes they will actually indicate the structure of your organization. And this is where something like Conway's Law comes in. So for those of you that haven't or aren't aware of what Conway's Law is, it basically says that the way that you design your systems will often reflect the communication structures that you have within your organization. And this sometimes comes about when you're having a look at systems, and you can see that actually there's a team that is looking after a certain set of microservices, and they will tend to be potentially sort of actually grouped together in some cases. But that's not the only way that that groupings may happen. There's a lot of different ways that this could be done. And a colleague of mine actually wrote a blog a little while ago, but it's on the various different heuristics that you can use to actually identify service boundaries when you have a microservice architecture. So there can be things, as I said, around the process and the data. So it could be that there are genuine bounded contexts, which you will sort of come across, but there could be data locality requirements. So maybe there's very specific data requirements, which means that certain microservices will naturally be grouped together compared to others. Or you may have technical or operational concerns, things like security constraints and stuff, which will also do that. So those are just some of the things that you might find the groupings come out with. So it's like, okay, that's great, but what happens if we change the architecture? So if we improve it, because we recognize we've got a problem, and we run these metrics again, will it actually show anything? Will we be able to see a difference? So if we recap, we already, we have our sort of V1 version of the architecture, and we know that we've got this entity services anti-pattern. So the first step in this particular case to try and sort of sort it out is we want to create an autonomous team that is actually going to handle user management independently of other things. So to try and make that happen, what we want to do is try and pull the functionality out of the single service and break it up into more sort of functional orientated services. So this could be things like update your user management preferences or disable the user or something like that. Then at the same time, what we want to do is we also want to refactor the front-end services. So we don't want all of the user-related functionality going in through the legacy sort of big ball of mud. So we pull those services out to make sure that any user-driven front-end activity goes through dedicated services. And in order to, we also at this stage kind of move to a more asynchronous or event sourcing sort of architecture. So this allows both sides of the puzzle to play nicely, or both sides of the architecture to play nicely. So the user management is done separately, but we also don't want to completely change everything that's in our legacy distributed monolith. So in this case, the information from the user is made available to the distributed monolith on the other side through sort of Kafka queues and or some kind of messaging software to allow the events and reconstruct the user on the other side. So in order to make that happen as well, there's where the old user service was, there's a bit of a facade there which looks a little bit like it did in the past, but that allows us to get the information from the newly separated domain and carry on. So if we take away the sort of the queues and the other databases and things like that, we're left with an architecture that looks like this. So this is our V2 architecture. And we want to do the same thing. So we want to run the network stats over them and have a look at what they look like. So if we start off with the degree, we can see that for our top offenders, as far as the degrees are concerned, we've still got the ones are highlighted mostly in the big ball of mud. But interestingly, we've actually seemed to have also got a high degree for our front-end services in the new area that we've created. And as I said before, this is not necessarily a problem, because if you think about it, you would expect that if a call comes into a front-end service, it is going to have to make calls to different functional back-end services in order to service that. So the fact that the degree is high for those new front-end services is not necessarily a problem. What we want to have a look at is the cluster coefficient as well. And when we do that, we can see that it's still highlighted most of the services in the legacy, big ball of mud. But crucially, it hasn't highlighted any of the back-end services in the new area that we've created. So, so this is good because we don't really want them to be talking massively amongst each other. When we run the community detection, we find that instead of just detecting 3 areas, it's now actually detected 5. And the previous sort of distributed monolith that we have, we'll see that actually it seems to have sucked in the shipping was the shipping API as well. And this is something that can happen with these algorithms. So they're not perfect, and it does require you as a human to have a look at the communities that have been created and see whether it makes sense for you or not. So at least as far as the main sort of orange bit is, red bit is concerned, you could say, well, it seems to have pulled in the shipping API or the shipping microservices as well. I'm happy with that. It still makes sense to me. I'm happy with the architecture. Or you might say, actually, maybe I do want to refactor that and make it a little bit more sort of decoupled as we have with the payment API in the bottom. But the key point for us is we look at the user, the new sort of user services that we pulled out, and this has got its own bounded context. So it's literally identified that this is actually an area which has now been able to sort of operate in sort of more isolation than it was before. There's also those 2 sort of services which seem to be floating around at the bottom there. And the reason for this is, as I said before, we also moved to a asynchronous architecture for the new side. So these are basically the listeners and or the consumers and the producers of some of the messages which are being sent across to the other side. And because we're only modeling the RPC-based calls here, they come out as orphans. So if we want to compare version 1 and version 2 of these architectures, we can see that we get something like this. So we've got version 1 is in green and version 2 is in yellow. The degrees are the bar charts and the dots are the cluster coefficients. And here we had our V1 user service that we were looking to refactor. This was split out into multiple different V2 functional services. And then, as I said before, we also had this facade or this legacy service which needed to be in the distributed monolith to allow it to continue. But when we have a look at the degrees themselves, we can see that not much has actually changed. They've stayed relatively the same. However, on the front-end services, we can see there's a little bit of change. So on the legacy side of things, the degree went down from sort of 5 to 4. And this is, as I said, for the sort of web API, front-end API, and the B2B API. And this makes sense because if you think about it, when we refactored the code, we pulled out the user-related functionality into a separate service, which meant that those services in the legacy distributed monolith side weren't actually making as many calls as they were necessarily before. So that makes sense. What happens though when we look at the cluster coefficient? So this seems to be maybe a little bit strange because the actual number seems to have gone up for us. And you would think, well, I would expect, or I would hope that this number would actually go down. And this should be going down would be a good thing to happen. But again, if you think about the areas, if you think about the architecture and how it's resulted, it does actually make sense. So again, these are on the front end, the legacy front end APIs. And what we did was we pulled all of the user information out of that. And the legacy side really just got a lot tighter. So there weren't all of the update calls that were happening in the user with user-related functionality before. So the cluster coefficient on the legacy side actually got stronger as a result of this refactor. But the more crucial thing is that, for the new services, the cluster coefficient doesn't actually even register. So that's a good thing. So there are various other things that you can sort of use, various other algorithms and things that you can use to do analysis. There's only so much that you can kind of fit into a talk. So that's what the ones that we've covered here. But some of the examples, other things you can look at are things like strongly connected components, which will help to detect things like a circular dependency. Also, you can use some of the pathfinding algorithms to detect things like deprecated services. And what you may find is if you use a distributed system, a distributed tracing product like Zipkin or something, it will often allow you to see these things. But again, some of the power that you can get is by extracting that information out, putting it into another database and then doing the analysis there. It can be quite powerful. So in conclusion, I think one of the things to say is that this is early days. So there's not a lot of people kind of looking at doing this at the moment. And you can't simply blindly apply the metrics that I've spoken about here on any architecture. It's a little bit like saying, you know, if you have unit testing of 75% or less, that's bad. You know, you're actually kind of doomed. It really is dependent on the architecture that you have and the particular problem you have in front of you. So sometimes there's a tendency to take the metrics and just apply them blindly. Absolutely can't do that. You need to use some common sense and understand your architecture in order to understand how the values actually apply. So architects are not going away, is still very much required in order to you know, build good systems and understand what's going on. So if we go back to our general hypothesis, what we're trying to see is, is there a way for us to move towards a more data-driven architectural improvements? And hopefully I've demonstrated to you that it is possible to extract some metrics and some KPIs from some of the tooling that we've already got, put that into a system which will allow you to analyze it, and then use things like graph theory to be able to have a look at and gain some insight into the characteristics of your architecture. Specifically, we used the metrics to try and detect if we could see if there was a tightly coupled architecture, or if it was tightly coupled sort of setup somewhere within the network that we have. And this allowed us to identify those areas, and then upon having a closer look, we recognize it as an entity services anti-pattern, and then you can try and do something about that. So we looked at 3 metrics. We looked at the degree, the cluster coefficient, and community detection. So the first 2 helped us to detect the sort of tightly coupled architectures, and the community detection really helped us to try and understand what some of the groupings were out there. So if you're interested in learning more about some of this stuff, there is a really good book from Mark Needham and Amy Hodler. They're the guys from Neo4j, called Graph Algorithms, and I would highly recommend that. And actually a shout out to Andy Bergen, and he did a talk not too long ago. It was actually a few weeks ago. He's the lead platform engineer at Sky Betting and Gaming. And he did a talk on looking beyond dashboards and actually visualizing complex systems. And in his case, he was specifically visualizing the Kubernetes nodes, sorry, the Kubernetes resources within a setup. So the nodes, services, all those type of things. And it's a really great talk. And it allows you to look at using some other tools, things like Gephi and stuff, for visualizing much larger microservice architectures. So I do highly recommend that talk. I thought it was quite good. And with that, that is me. So yeah, I hope that was helpful. I think we'll probably go to some questions now. I've got to figure out how to do that. All right. Cool. All right. So I think we're going to questions. I just have to work out how we do that. Unless somebody can tell me how this is going to work. All right. Are there any questions out there that people want to ask? I'm looking in the chat. Or you can unmute yourself and ask. I'm not sure how this actually works. So.
Hi, can you hear me?
I can hear you. Yeah.
Just a quick question. So great presentation, thanks. A logical extension of a graph is a weighted graph, and maybe a weighted graph comes out of the notion of chattiness. My question is, are you developing any ideas in that area? Do you see any potential for that?
Absolutely. I mean, I think, like I said, this is to try and get some of the general sort of concepts across, but having the weights in the graph is very much a key part actually of graph theory. So, and again, you could get that from things like how many times a service is actually called, and use that in order to change the analysis that you do. So there's quite a lot of different things that you could actually do. This is a, you know, sort of a few of them that you could have a look at, but weighted graphs is definitely something to look at.
Thank you.
Cool. Anyone else got some questions? So just looking in the chat, oh, it's going a bit fast. Wouldn't the metrics you use identify the monolith as a best solution? Not necessarily. So, I mean, in this case, there were problems with the fact that things were too hard to sort of release together. It was unable to release one thing without releasing 101 other things. So if I understand the question correctly, the metrics are not there to try and suggest one solution over another. What it is there to do is to try and point out patterns in a network that you know are problematic. How you solve that solution afterwards, or what solution you use to solve that, would depend on a number of things. So you might choose to go to a monolith. That might be an option. Or you might choose to structure things differently. So the metrics wouldn't necessarily identify a monolith as the best solution. All it can do is say, in this solution, there's a lot of chattiness going on here, and you may want to have a look at it. Has this been offered as a consultancy offer, and how has the market responded? Which industries are more keen to re-architect their legacy? So this is not specifically offered by us as a sort of consultancy thing. It's part of what we do in consultancy, to try and have a look at architectures and things. Like I said before, you can't throw out your common sense and a lot of the information and understanding that people have grown up with. This is very much early days. So it's one of the things in the toolbox to have a look at. In terms of the sort of market response, so some people are quite interested in this. So the guy I spoke about previously, Andy Bergen, so he actually referenced this talk, and I'm referencing his talk now because I think it's quite interesting. So I think there's a desire to look at it, but it still needs more work to try and see how effective it can be in a lot of different architectures. Are there any products that do this already? I don't think so. can you mention some of the automated ways to generate a graph, please? Mainly for Kubernetes, GCP, AWS, Python legacies, and Java legacies. So if you have, so for Kubernetes, Andy's talk is in one way a good example, because you can actually just hook into some of the APIs and write some code in order to extract the information and put that into a graph. So you might have to write some code yourself in that case. If you have GCP, AWS, Python legacy. So I'm not sure I understand the question completely, because I think it depends how you deploy your microservice within GCP, if that's within Kubernetes or if it's just on boxes. This is why there's no one size fits all. So the automated ways of generating a graph are by hooking into some distributed tracing system like Zipkin, a service mesh like Istio, or actually writing something that can suck the information out. So people have done that before. Cool. All right. So how does it relate to the multiplicity of instances in specific nodes in an HA case? So I guess this is where you might have 3 instances of a particular service that are being used in order to, yeah, maybe a service is really sort of big or it requires a lot of effort and you need 3 services instead of 2 services. This particular modeling doesn't necessarily take that into account. At the moment, it's just looking at the architecture. So what is calling what? That's another level that you could go down at as well to try and work out through things like maybe if you've got weighting in a graph, this is something we could say, actually, this path is really, this is quite a path where a lot of traffic is going through. So maybe that could help as an indicator to say, maybe I need to have more instances in order to take or accept the traffic. So that could be a way of looking at things. But the modeling itself doesn't, in this particular case, model the instances of an individual service itself, although you could do that as well. So I think we're probably almost out of time. So I hope that was helpful to all of you. Did it make sense? I hope it made sense. Yeah. All right. Excellent. I see a few nods. Hopefully a few stares. So we'll hopefully it made sense. Excellent. All right. I'm not sure who the host is, but I don't know if you want to. Any other questions, or otherwise, I guess we'll close it down. All right. Cool. I think we're done. Thanks, everybody.
Thank you.
Thank you.
Thank you.
Thanks.
Thank you.